Hi, this is Matt Pelland here to talk about the work I've done for OPL recently. So the first thing I have to talk about is my CESK machine. So the CESK machine that I constructed is actually fairly different from what we did in class because I wanted it to be backwards compatible with the previous iSwim, and I also didn't want the programmers to have to be constantly dereffing variables whenever they wanted to use the values within the variables. So what I did is I set it up to automatically dereference pointers in all scenarios except when you're trying to set a variable to a new value. So that's what's going on right here, is that if we're looking at a pointer in the machine, then in every scenario other than when you're setting that variable to something, it'll automatically dereference that variable by accessing the store indexed at the current pointer and then continuing evaluation. So in this way, deref is completely unnecessary and isn't used at all in my expressions. So obviously this is a little less powerful because you can't pass around pointers because they aren't exposed to the programmer, but in my opinion it's a lot neater, it's easier to write, it's easier to read the program and see what's happening without all those derefs, and it also makes it backwards compatible so that this CESK machine can run any expression that my CEK machine could. And then other than that, it's very similar to the CEK machine except for the set, obviously, which will first evaluate the variable that's trying to be set to, and then it will evaluate the value being set to the variable. Excuse me. And then once you're actually setting, that is done right here. Or once you have a value and your continuation is the value for the set, then you access the store at the current pointer, which is stored in the set val continuation, set it equal to whatever your value is, and then continue evaluating. So this wasn't too bad. It was basically just following all of the rules that we discussed in class, very similar to structuring the CEK machine with just the addition of the set overriding the store, and the fact that when you're accessing a variable, you return sigma sum the variable, which returns a pointer, which will then either be immediately automatically dereferenced or sent into the set continuation. So this is fully functional, and I'm going to get back to testing it because I integrated my examples with the type checker that I wrote for along with the CESK. So this is just the vanilla type checker as we initially discussed, where for every given expression it will call the type checker on the subcomponents, and if you're given, say, a constant, then you have the big delta function, which will, in the case of a constant, it just returns, if it's a number, then it will return num type. If it's a boolean, it will return bool type. And then similarly for operations, it will, first of all of the operations I have are solely for numbers or solely for booleans, so I just set those in two arrays for it to index. And if it's a number operation, then it checks that all of the arguments have a type of number, otherwise it will return none type, and it does the same for booleans. So my types are just a few classes where it has the overarching abstract class for type, and then base type covers your constant values like numbers and booleans, and then we have a map type, which itself holds two types, and then there's none type, which I just use to indicate if the program has no type. And so that will be returned in scenarios where the type checker fails, such as when you have a number operation but you try to pass the operation a boolean. Excuse me. Or if you have an application and your function of the application is expecting a number and it's passed a boolean, that will trigger this, which will return none type. So it just goes through, and in every case where there's multiple components, it'll just call the type checker and make sure that it satisfies any constraints that exist. So that was pretty basic. And I also added in ifs, which in this case will call the type checker on each of the components, and it'll make sure that the boolean that's passed to the if that it's checking to determine which of m and n to run is in fact a boolean. And if it's not, it will return none type, and then it also makes sure, in this case, that both of the possibly executable expressions return the same type of value, because that was just how I decided to implement the ifs rather than doing the unions, just because it was simpler. So what I have here is just a very large test function that I created to run essentially everything. I have the large test that I had previously for my CEK machine, so that exact same test is being fed in with the addition of the typing for the abstractions. And then I have some more tests that work with the ifs and bools that I added. And so I have a giant test that uses the ifs, it uses the booleans, and when you run it, it correctly identifies. That's running the wrong thing. No, there we go. So this is the giant expression I have, and as you can see, what we're passing it is we're passing true to this if, which just negates it and then calls the if, and so that will evaluate as false, and it is then calling this expression, which uses my set, where it takes whatever value is passed in, and then it sets it equal to 2 times itself, adds that to itself, and then multiplies that by 2 again, and adds that to the net sum. So you can see we're passing in 4, so that's evaluating to 4, and then it sets x to 2 times x, which is 8, and then adds that, getting a total of 12, and x is now 8. And then we multiply x by 2, and add that into the sum, so that 16 plus 12 is in fact 28. So you can see there that the set is properly changing the values of the variables for future expressions. And then, excuse me, if we swap this value to false and run again, then the if will trigger and run the other expression, which is the same test expression I had for my CEK with the addition of the types for the abstractions. But other than that, the addition of the mutation didn't cause anything to break here, as it would if I had implemented deref, as we discussed in class. But you can see even without the derefs, using my CESK, it still runs the exact same code and produces the same output and works perfectly fine, because 18 is in fact the correct output of that expression. So as you can see there, my type checker and CESK machine are in fact fully functional. And if I were to put, say, a number here where it expects a boolean, then you can see it has no type because it was expecting a boolean but received a number, and the type checker properly detects that, and as such it cannot be computed because it would become stuck. And similarly, if I pass a boolean to this function, which was expecting to this operator, because it is the times operator which cannot work with booleans. Let me just fix this back. It will correctly detect that a boolean was passed to a number operator, and it will return that it has no type. So it's properly detecting all failures as well as correctly evaluating the types of correct expressions. So the next thing that I did was to implement type inference. This one, the only real change that I made relative to what we did in class is the generation of variables, in that I have, where is it? I have this function newVar, which accesses just a global counter and indexes it by 1 every time, and then I have a class typeVar, which has within it an ID, which is that number. So every time you need a new variable, it will just increment that global value and create a new typeVar with that ID. And in the manner that I did this, it ended up such that I didn't need to keep track of variables within the constraint generation. So my constraint generation creates these inference objects, which just have their associated type and their associated list of constraints, and it didn't need to keep track of the variables as well because they're simply the set of all variables up to the current var index. But beyond that, it was just the general, exactly as we discussed in class, format of generating constraints, where, for example, if it's a constant, then we create this inference object whose type is going to be big delta of whatever that constant value is, and it doesn't create any new constraints. In the case of a variable, it accesses gamma sub whatever that variable is to determine whatever the type is, because gamma maps those variables to their associated types. Then if it's an application, you generate constraints for both of the two components. You create a new variable, which is the output type of this application. When you create, I just created a new inference and then added the constraints to it. And then I added the one constraint that whatever the function is expecting as an argument is in fact, the function itself, its type is going to be a map from whatever the argument's type is to whatever this new R is that we're assuming the application will return. And so that's the guessing that kind of happens there. So it is really just what we discussed, but then the operation was also fairly straightforward in that we determined which kind of expression it was, whether it's a number operation or a Boolean operation. And if it's a number operation, then for every expression in the operation, we add the constraint that it has to be a number, and we do likewise for Booleans. And then if we're doing set, I made the ruling that if you are setting a variable to a new value, the value has to be the same type as the variable's original value. So you cannot set x to 5 and then later set it to a Boolean. So for that, we just say that whatever the new value is that we're setting it to, we make sure that it is the same type as whatever the variable currently is. And then for the ifs, we simply make sure that we add the constraint that whatever the Boolean is that's being evaluated is in fact a Boolean, and we constrain that m and n both evaluate to the same type of value. So that was just all of the constraint generation that we have, and then solving the constraints is exactly the rules that we discussed, where if they're the same, if it's saying like a equals a, then obviously that's vacuously true and you can just ignore it. If it's a map type, you create the two constraints setting the input type and the output types equal to each other, etc. Just exactly as we discussed. There was nothing really special going on here. So then I just wrote, these are just some functions for running it and getting some neat output. So for example, I have this map test, which is just a function. And as you can see, it evaluates, still running the old code, there we go. So you can see here it is correctly identifying this as a function that maps a Boolean to a Boolean. In this case, it just returns the same Boolean. And when you run that, you just get back the same lambda. But then if I run with the same output as before, the large test, it is the same expression and it still correctly identifies it as a tnum. And when run, it still identifies the correct value output. Though notably, we no longer need those types to be associated with the abstractions. So using type inference with my CESK machine is fully functional on the original iSwim functions that we discussed. And that was really what I was aiming for when I was working with these projects, was trying to make a CESK type inference system that could work perfectly well backwards compatibly with all old iSwim programs. So that's what I've got. Thank you.